So today we're going to be talking about multi-step mole calculations. In your packet, I believe it's on page 20, I actually put something called the mole road. Some students find this helpful. It's kind of a nice little thought process. If a question starts you at particles, that kind of reminds you that you're going to have a step where you go to moles before you can go to where you want to end up. So if you want to end up in liters, you would then go this way. If a question started you in particles and wanted you to go to grams, you'd then have to go this way. If you start with moles, you can really go either way at that point. But you can kind of use this little roadmap. If you start at grams and you need to end up at particles, you do this step first, and then you go this way. You can go either way on the mole road. You just have to think about what that means in terms of your conversion factors and what you'll put on the top and bottom. For each of these, I have gone through and found the gram formula masses already. So oxygen gas, remember, is O2, so I went ahead and doubled the mass of oxygen from the periodic table. I mainly did this in an effort to keep recording, although I don't have calcium chloride, so I will have to quickly figure that out. But I mainly did that to just kind of keep the video rolling. So when you have a question where you have multi-steps, meaning I am starting with liters here, and I need to end up in mass, which means I'm going to have to start here, go through moles, and then go over here to get to mass. So I know that I have a multi-step problem here. I'm doing more than one thing. This is pretty easy using dimensional analysis. We're starting with our 78.62 liters that the problem gives us. My first thing that I'm going to have to do, and if you like this kind of mole road model, you can look back at this and say, okay, I'm at liters. I'm going to use this 22.4 conversion factor to get into moles. So liters is going to need to be on the bottom so that I am then able to cancel out liters. Now I'm in moles and I need to take this into grams. So that's where my GFM is going to come in of my 31, I kind of made it tiny up here, 31.9988 grams per mole. I'm going to need moles on the bottom in order to cancel moles. And my grams on top. Now my moles go away. So this satisfied us going from moles into grams using the GFM. You can go ahead and punch that into your calculator, and you should get 112 grams. The 22.4 is limiting our number of significant figures. I'll pause for just a minute to find calcium chloride's gram formula mass before I do the next question. Sorry about that. Okay, so calcium chloride, remember, is CaCl2, which gives us a gram formula mass of 110.986 grams per mole. We're starting here with grams, and we're going to take this into molecules. So to go from grams into particles, we're going to use first our gram formula mass to get into moles. So we're starting here. We got one step to get us into moles. Then we're going to take one more step to get into particles. So in order to do this, we're going to write our starting amount first, 51.61 grams. To get into moles, we're using our GFM, and we do have grams on the top, so we're going to put our 110.986 grams on the bottom and 1 mole on the top. Grams will now cancel. Now we have moles, we need to take this into molecules. So 1 mole goes on the bottom. 6.02 times 10 to the 23rd molecules are just going to go on top. Moles are going to cancel. So then you're just going to do 51.61 times 6.02 times 10 to the 23rd. Remember, you're using that little e to show that. And that should give us, actually I have one extra sig fig there, sorry. 2.80 times 10 to the 23rd molecules. You could actually plug this in with another 2 if you want to get that extra sig fig, but typically we'll just limit that to 3. Sample of sodium nitrate. Remember, sodium nitrate is NaNO3. The sample has a mass of 198.9 grams. And we want to actually take this into atoms, which is going to involve an extra step. So we are going to first get our grams into moles. So we're putting our 84.99467 grams, turning that into 1 mole. Grams are going to go ahead and cancel. In our next step, we need to take moles into molecules. So remember, NaNO3 is made up of multiple atoms. So sodium's an atom, nitrogen's an atom, each of those oxygens are atoms. So the first thing we're going to do is take 1 mole and change that into molecules, which means that whole group. So this is actually referring to a whole group of NaNO3. We want to know individual atoms. So we have to look at how many pieces make this compound up. 1, 1, and 3. So 1 sodium, 1 nitrogen, 3 oxygens. So 3 plus 2 is 5. 1 molecule of that compound contains 5 atoms. So this will allow us to cancel our moles over here. We canceled our molecules here. Sorry, that look more like atoms. So you're going to do 198.9 times 6.02 times 10 to the 23rd times 5. And you're going to be dividing that by 84.99467. Which should give you 7.0. I kept an extra sig fig there again. I'm sorry about that. So this is, sorry. This is actually going to round up to a 5. So this is going to be 7.05. Being lazy about my sig figs this year. Times 10 to the 24th atoms. I'm going to just kind of move this up a little bit so we can look at our last question. How many liters are occupied by 726.17 grams of carbon dioxide? So we're going to start with our 726.17 grams. And we're going to first turn this into moles. So I did the gram formula mass already. 44.0098 grams is 1 mole of carbon dioxide. Cancel out our grams. Moles are easily taken into liters by doing 1 mole on the bottom and 22.4 liters on top. We're going to go ahead and we're going to cancel our moles. So this is going to be 726.17 times 22.4 divided by 44.0098. And this should round to 370 liters. Please notice that decimal there to give me my 3 sig figs that I should have in my answer for this. So I'm going to pause. Sorry about that. So what we did there was we took grams, we went into moles, and from moles we then were able to go into liters. So we did that as a 2-step problem. The last 2 up here that we're going to do in the video today, how many molecules of CO2 are contained within that sample. So we're actually going to take our amount that we had over here. You could kind of just chop off the end of this one and you know, take what you already have. This part of this calculation is actually going to be the same. So you could just kind of continue from there. I'm going to just kind of carry the amount over the 726.17 and start it all over again. So I've got 726.17 grams. Again, I need to get that into moles. After I've turned that into moles, I want to go straight to molecules. I'm not really worried about atoms or anything here, so I can just go straight 1 mole, 6.02 times 10 to the 23rd molecules. That will make my moles cancel. I have my answer in the unit I want. So I'm going to do 726.17 times 6.02, E23, and divide that by 44.0098. And that should give you, again, I kept an extra sig fig here. I'm sorry about that. Should have edited this before I made the video. So you should get 9.94 times 10 to the 24th molecules. The last one's a very tricky question. So we actually want to take barium nitrate, we know its mass, and figure the atoms of just oxygen in it. So take a minute, go ahead, pause the video, and give this problem a try. I'll put the answer up in just a moment. So for this problem, you should have gotten 2.28 times 10 to the 24th atoms of oxygen. So we started with the grams and did the mole conversion first. We then take moles into molecules in this step. And then looking back at our formula for barium nitrate, we're looking at 6 oxygen atoms in each molecule. So once you do your calculation, you should get 2.28 times 10 to the 24th. I'm going to be working on these a little bit more in class as we move forward.